my name is Samir Khan and I'm the MapleFlow product manager. In this webinar, we're going to talk about 5 electrical engineering calculations. We'll look at them in MapleFlow, the calculation tool for design engineers. The examples have been chosen to reflect a broad range of mathematical concepts. These include numeric equation solving, symbolic math, linear systems analysis, signal processing, and more. For some applications, I'll just quickly run through some of the basic principles, then talk you through the complete worksheet. In others, I'll type a few commands into a half-completed worksheet, and I think for maybe 1 or 2, I'll create the complete applications from scratch, hopefully not making any mistakes along the way. So let me just dive straight into MapleFlow. So the calculations that we're looking at today are circuit analysis and amplifier gain, denoising a signal, worst case circuit analysis with Monte Carlo simulation, double stub matching, and parameter estimation for a photovoltaic diode. Let's start off with some circuit analysis. Let's talk about some principles first, some relevant Maple commands. When you're deriving and manipulating circuit equations, there are several really useful Maple functions, and we'll go through some of them now. Quite often you'll end up with circuit equations that you need to rearrange. So I already have this circuit equation typed into Maple. Let's say I want to rearrange this to give me an explicit expression for VC. The solve function can help me with that. I simply wrap the whole thing in solve and ask it to give me an explicit expression for VC. So there we go. If I want to use the result downstream in my analysis, I can simply assign the result of this to a name and use that assigned name elsewhere. That was a very simple example for solve. It's capable of doing a lot more. You actually have access to some really advanced mathematical functions and algorithms in solve. These are algorithms and functions that you normally wouldn't typically encounter in an engineering math course. This, for example, is an equation for a photovoltaic diode. A number of parameters in here, but the most relevant ones are IF, the experimental current, and VF, the experimental voltage. Let's say I want to rearrange this equation to give me an explicit expression for IF. Well, using traditional techniques, that would be difficult to do because IF appears both outside and inside this exponential. Let's see what I can do with solve. So let's solve this for IF. And it gives me an explicit expression for IF in terms of the Lambert W function. That's what we call a special function. It's traditionally only used in mathematical research, but MapleFlow lets you use this function very easily. Also, you'll need to simplify expressions to more compact, more readable, but equivalent forms. Let's take this transfer function. It's not presented in the simplest possible form, the most compact form. But the simplify function can help me with that. This is a user-created function. It calculates the action of resistors and capacitors connected in parallel. So if I have 2 resistors connected in parallel with resistances of 2 and 3 ohms, the resulting resistance would be 1.2 ohms. This works with units as well. So what I could do is add a unit to this. The resulting resistance is given in ohms as well. If I wanted to, I could rescale this to any equivalent dimension, let's say kilo ohms, with the context panel. So I simply open the context panel and type in my desired unit here. And let's add in some numeric formatting. That's simple enough. So here I have a transfer function. If I want to evaluate the DC gain, I need to substitute s equals 0 into this, and I can do this with the eval function. So let's evaluate this transfer function at s equals 0. There, the DC gain is 2. I'm not just restricted to substituting in numerical values. I can make more complex substitutions as well. So let's replace s with 2 pi omega. And there we go. By the way, MapleFlow has approximated pi with a floating point number, but if I don't want that approximation, if I want to see the actual value of pi, the Greek letter, what I can do is toggle the symbolic toggle on here. So if I click on this math container, go up here and click on symbolic, MapleFlow doesn't perform that approximation. Sometimes I'll also need to convert transfer functions from the S domain but to the T domain, and I can do that with this function. So I'm simply taking this transfer function and converting it to the time domain. That's a simple example, but it's capable of doing more complex conversions. Let me just try this. So there we go. Again, MapleFlow has converted the rational numbers to floating point approximations, but let's toggle this math container to symbolic, and there we have a more meaningful result. There's also a whole suite of tools in MapleFlow for the analysis of linear systems. You start off by creating a dynamic systems object. Dynamic systems is the name of that package of commands, and that object can be a transfer function, a differential equation, a state space model, or something else. You can then use tools from the dynamic systems package to analyze that object. There's a whole suite of commands, but I've just found out the command completion menu, and I think I'll create a plot. Let's say Nichols plot. There we go. Let's expand this. So here I also have a phase and magnitude plot. There are several options which allow you to fine-tune the look and feel of this plot. So the frequency axis is given in radians per second. If I simply wanted hertz, I could do that quite easily. If I don't actually want to see the plotting command, if I only want to see the plot, I can right-click on any plot and select hide command. Let's do that here for these plots. And now if I change this thing here, the plots update, but I don't see the command used to create them. Let's change that back. If I want to do some stability analysis, I can calculate the phase and gain margin. And there's a whole suite of other tools in MapleFlow for symbolic math, symbolic analysis of expressions. Let's say for the sake of example that I wanted to convert this to a partial fraction. That's how I do it. We're not going to cover any of the other symbolic math functions right now, but what I will do now is actually close down this document and let's talk about this application. So in this application, we're actually plotting the gain of this amplifier circuit for both the ideal and the non-ideal response. This is simply a diagram, a picture that I imported from a picture file on my computer, but on the right-hand side, I've defined some parameters, some resistances and some capacitances. So here's that function I introduced earlier for calculating the effect of impedances connected in parallel. And I'll start off by analyzing this part of the circuit here on the left-hand side, R1, C1, and Rin. Well, the impedance of R1 and C1 is simply R1 plus 1 over S times C1. If I want to connect that in parallel with this resistor Rin, I do that here. Again, this result isn't necessarily in the simplest possible form, so I'll use the simplified function. I'll wrap this in simplify, and there we go. A much more compact but equivalent representation. So I do that same process for the other parts of the circuit, and I end up with an expression for the ideal amplifier gain. If you look carefully in this equation, there's a very small floating point term here. It's not going to do much to the dynamics of the system. So what I can do is remove small floating point numbers with the f normal function. So if I press enter now, there we go. That small floating point term has disappeared. So I carry on, I calculate the non-ideal amplifier gain, and then I plot the frequency response of both the non-ideal and the ideal response. I have two phase plots here, created with tools from the Dynamic Systems package. Of course, if I want a more meaningful comparison of both the non-ideal and the ideal response, what I really should do is plot one plot on top of the other. I can do that easily. So I'm going to assign the result of this plotting call to P1. Let's remove some white space there. I'll assign the result of the second plotting call to P2. And now I can overlay one plot on top of the other with the display command. And there, let's increase this in size. And you can see that the non-ideal and the ideal response only really differ at the higher frequencies. So let's move on and let's talk about our second application, signal denoising. In fact, I think I'll create this one from scratch. Let's see how this goes. So let's fire up a brand new MapleFlow document. So what I think we're going to do, I think we're going to artificially create a signal. Perhaps the sum of two sinusoids. We'll pollute that signal with noise. We'll look at the frequency content of that signal with a periodogram. And then we'll try some frequency domain filtering. We'll see if we can remove the effect of that noise. All right, so we'll artificially generate a signal with 1000 elements. The sinusoidal signal will have two frequencies, f1, 3 Hertz, and f2, 60 Hertz. And we'll need to define the sampling rate. That's like 500 samples per second. So there's a really useful suite of tools called signal processing. And there's one particular function called generate signal, which allows me to generate a discretized signal from an algebraic expression. The first argument is simply an algebraic expression that we're going to sweep. So it'll be the sum of two sinusoids. And we're going to sweep this algebraic expression across T. The second sinusoid will have a frequency of f2. We're sweeping this across T at a sampling rate of 500 samples per second, and we want n samples. So let's evaluate this and let's see what we get. All right, it's returned a vector with 1000 elements. That's the discretized signal. Of course, I think what we really want is the vector of times and a vector of signal values as well. And I can do that if I remember the syntax. So we want to output times in the signal. And if I've done that correctly, we end up with two vectors. The first containing the discretized value of time and the second containing the discretized signal. So let's assign the result of this to times and signal. We don't need to see these two vectors, so let's remove that equal sign. And let's move this up and get rid of some white space. Let's see what the signal looks like. All right, let's increase the size of this plot. So if I've done this correctly, we should see the lower frequency and the superimposed higher frequency as well. I think I said I was going to pollute the signal with noise. So let's start off by creating some random data. I'm going to create a random vector with n values. Each value will be uniformly sampled between -0.5 and +0.5. And below this, I'm going to say signal is equal to the signal plus the random noise. As soon as I hit enter, you should see that my signal has some random noise now. If I increase the magnitude of this random noise by a factor of 5, there, it's a lot more noisy. So let's just examine what this signal looks like in the frequency domain with the periodogram. For the frequency scale on the periodogram, we need to specify the sample rate. And there we go. Let's increase the size of this, move it into position. So we have frequency on the x-axis against the power in decibels on the y-axis. If you look carefully, you can see that there are two peak frequencies, a lower frequency and a higher frequency. Of course, I think to make this more meaningful, what I want to do is actually rescale the y-axis from decibels to the absolute value. There, that's much better. So we can clearly see that we have two peak frequencies together with lots of low-level noise. If I actually go up to here and I change the value of the frequencies used to generate the sinusoid to 10 Hertz, and let's say 100 Hertz, press enter, you see that reflected in the periodogram. All right, so let's try to zero out the low-level frequency. So I'm going to start off by taking the FFT of the signal and then the power spectrum of the FFT data. So we're going to create a new vector, which we selectively fill with data from the FFT. If the nth value of the power spectrum is greater than a threshold value, we'll keep the nth value of the FFT, but we'll discard it otherwise. We'll need to define a threshold value. So we're going to remove anything below a power of 50. So let's create that filtered FFT data. So it's a vector with n values. And if the power spectrum of a particular frequency is greater than a threshold value. We're going to keep the data from the FFT. Otherwise, we're going to discard it and replace it with 0. Let's hope I've done this correctly. So let's now invert that filtered FFT data to the time domain. I know the time domain signal will have very, very, very small imaginary numbers in there somewhere. So I'm going to only extract the real part of the inverted data. All right, so now if I've done this correctly, what I should be able to do is plot the times against the clean signal. And let's expand this. And let's plot this alongside the original noisy data. So you can see we filtered out a lot of the noise. The signal is a lot smoother. Of course, once I've created an application like this, I might want to present it nicely, convert it to a PDF. So what I can do is go to the View menu, select Print Extents. I see vertical and horizontal dashed lines. These delineate the boundaries of my chosen page size. So I'm just going to shift everything about, change the size of plot so everything fits neatly within a page boundary, including these two plots. I'll break this equation here so it doesn't spill over the line. I'll move it up. I could also add in some text comments as well. Now, once I've formatted my document neatly, if I want to convert it to a PDF, I can go to File, Export As. If I simply want to see what it looks like on the printed page, File Print Preview is my friend, and there we go. It's a faithful reproduction of what I have in my canvas, my worksheet. Let's close this down and let's talk about worst case circuit analysis. You can actually implement several techniques for worst case circuit analysis in MapleFlow. These include extreme value analysis, Monte Carlo simulation, sensitivity analysis, optimization, and root sum square analysis. Let's talk about some principles first. I think we'll talk about extreme value analysis and Monte Carlo simulation. So for extreme value analysis, I need to evaluate the operation of a circuit at its extreme tolerance values. So for a circuit with 3 components, I need 3 nominal values here and 3 symmetric tolerances here. We then have to generate every combination of extreme tolerance values. Since there are 3 components, there are 2 to the power of 3 or 8 combinations of extreme values. This thing here, this math container, it's a bit dense, but it essentially gives me a vector zeta with 8 elements, each element being a vector with a unique combination of 3 extreme tolerance values. And here I extract out the individual vectors of extreme tolerance values. All right, so then I have a circuit model. So this is a simple voltage divider model. And then I multiply the nominal values against each combination of extreme tolerances to end up with a vector of extreme values. Let's see what that vector looks like. There we go. And then I can use the min and max functions to extract the minimum and maximum voltages. So those are my extreme voltage values. So with a simple extension of this technique, you could also implement asymmetric tolerances as well. Moving on to Monte Carlo simulation. MapleFlow lets you work with about 30 or 40 standard probability distributions. They can either have symbolic or numeric parameters. So here we just start out with a simple symbolic probability distribution, a Weibull distribution with a shape and scale parameter of A and B. Using tools from the statistics package, I can calculate the mean and the standard deviation and the kurtosis. If I change this to a normal distribution with a mean of A and a standard deviation of B, it won't surprise you to know that MapleFlow tells you that the mean is A and the standard deviation is B, and the kurtosis of any normal distribution is 3. Of course, for Monte Carlo simulation, I need to sample those probability distributions. I can do that as well. So here I'm going to generate 1,000 samples for a normal distribution with a mean and a standard deviation of 4 and 5. And here's a histogram of the resulting sample data. If I change n to 100, the histogram is a lot coarser. If I change n to 5,000, the histogram is much smoother. So let's use those techniques for Monte Carlo simulation for some worst case circuit analysis. Let's just dive straight into this application. So in this application, I'm actually going to use Monte Carlo simulation to perform worst case circuit analysis of a photodiode circuit. So this function gives you the output voltage in terms of 9 parameters. Each component, each parameter has a resistance or capacitance defined by a normal probability distribution with different mean and standard deviations. You sample each probability distribution to end up with your randomized data, and then you simulate the output voltage of the circuit by calling this function with each of these sample data sets. You can then use MapleFlow's tools from the statistics package to extract the results, the mean and the standard deviation. And then if you're so motivated, you could create a plot that looks a bit like this. This is actually created from 3 individual plots overlaid on top of each other. The first is actually a histogram of the simulated results. That's the blue bars. The second is actually a density plot of the normal distribution with the mean and standard deviation calculated from the simulated results. And the third are 2 vertical red lines, which indicate 1 standard deviation from the mean. If I wanted 2 standard deviations from the mean, I could do that simply by making a couple of changes. I press enter, there we go. The red lines now indicate 2 standard deviations from the mean. So let's move on from this and let's talk about stub matching. Let's just go straight into the application. So electrical engineers sometimes need to match the load and to the impedance of a transmission, numerically solving a nonlinear set of equations. That actually requires strong numerical solvers. And the use of numerical solvers actually supersedes traditional approaches using Smith charts. There are ways and means of generating Smith charts in MapleFlow, but we won't cover those in this session. The parameters in stub matching problems have dimensions. So for example, the load and the impedance have units of ohms, the wavelengths and the position of the stubs have units of meters. We want to calculate the value of L1 and L2. So this is the circuit equation. To balance the problem, to calculate the value of L1 and L2, the real part of the circuit equation must equal 1, and the imaginary part of the circuit equation must equal 0. So we're going to progressively refine our solution method. So if you start doing this, you might naively do something like this. We want the real part of the circuit equation to equal 1, and the imaginary part of the circuit equation to equal 0. Let's evaluate this and let's see what it gives us. All right, well, it's given us results for L1 and L2. They're mathematically correct, but they're not physically correct. They're complex numbers. Let's add the stipulation that L1 and L2 are real. There. L1 and L2 are now real numbers, but they're still not correct. L1 is negative, L2 is negative as well. So what we probably need to do is give the numerical solvers a nudge in the right direction with guess values or initial values to start working with. So we're going to guess that L1 is about 0.1 meters. And L2 is about 0.1 meters as well. Made a mistake, you'll bear with me. Oh yes, there's a comma there, not a decimal point. There. And now we have realistic values of L1 and L2. So we could extract the values of L1 and L2. We could use them downstream in our analysis, but let's just move on to our final application. Parameter estimation for a photovoltaic diode. Let's talk about some principles first. We'll need to do some nonlinear curve fitting. So we'll need experimental data. That experimental data could be imported from a spreadsheet, a text file, or something else. But here I've just entered my experimental data in two vectors, X and Y. And this is my equation I want to fit. X is the independent variable, and A, B, and C are empirically determined parameters. If I want to fit my equation to my data and find the best values of A, B, and C, what I can do is use the nonlinear fit function from the statistics package, give it my model, my X and Y data, and the independent value, the independent variable. And there we go. That is my best fit equation. I can now assign this to a name and plot the result if I was so motivated. Let's close that down and let's just jump straight into the final application. All right, so this is my photovoltaic diode circuit. Again, this is simply an image that was imported from another application. This is the equation for a photovoltaic diode. I think I might have shown you some form of this equation earlier. First of all, we need to rearrange this equation to give an explicit expression for the experimental voltage, IF, in terms of the experimental current. We can do that with the solve function that I introduced earlier. There are some parameters that I know and some parameters that I don't know. So the parameters I know are given here. So let's see what the circuit equation looks like when I substitute these numbers in. So here we go. There are still some undetermined parameters in this equation. If I actually want to find what those undetermined parameters are, I can use the index function to give me all of the unassigned names. And there we go. So I want to find best fit values for ISD, IPH, RS, RSH, VF. So VF is actually my independent variable, and N. I then start by importing some experimental data from a spreadsheet file, a .xlsx file, and I plot that data here. And then I use the nonlinear fit function, which I introduced a couple of minutes ago, to find the best fit values of the undetermined parameters. And then, as the final flourish, I plot the experimental data against the calibrated model here. It's a pretty good fit. So that brings us to the end of this presentation. This has been a brief run through of 5 electrical engineering calculations. The calculations demonstrate a broad range of concepts, including numeric and symbolic equation solving, plotting, signal processing, Monte Carlo simulation, statistics, and regression as well. If you'd like to know more about what Maple can do for electrical engineers, then I do recommend that you browse our landing page for electrical engineers. The address is given here. It contains more details and links to an application gallery, which allows you to download some electrical engineering worksheets from MapleFlow. But with that, I'd like to draw a line under this presentation. Thank you for listening.